my name is Jim Hazzard. I work for Itasca Consulting Group in Minneapolis. Today I'm going to talk about numerical modeling in rock mechanics from continuum to discontinuum. Really, this probably should have been called numerical modeling in rock engineering. My plan here is to show some of the different numerical modeling methods and then show some real-world examples from some consulting projects that we've done here at Itasca. I thought it would be interesting to start by looking back at this paper from 20 years ago. This was Peter Kundal, and in January 2001, this was published, A Discontinuous Future for Numerical Modeling in Geomechanics. And in the abstract, this quote says, the application of particle methods to large-scale problems is currently difficult or impossible because of high computational demands. It is shown that such applications should be feasible within 10 years and certainly within 20 years. So I thought it would be interesting to look at this because now we're at 20 years and see how accurate this prediction is. If you cast your mind back to 2001, you'll remember that we had no 64-bit computing and no multi-core machines. So certainly computational power has come a long way since then. So at a high level, here's the different types of approaches I'm going to talk about. Continuum approach, this is probably the most popular still. You assume that your rock is a continuous material that can deform and hold stress and so on. It's possible to include a few fractures or faults, but in general, you're assuming a continuous material. On the right-hand side, you have a true discontinuous material where you have a bunch of pieces that are not able to deform, and these can only interact at their points of contact, and then you get rock behavior from these contact laws rather than from the sort of continuum laws. And then in between, you have this, what I'm going to call the hybrid method. And what you've got here is pieces that can interact with each other as in the discontinuum method, but the pieces themselves can deform, and they're like little continua. And so it really is a hybrid between discontinuum and continuum. So if I just expand on this a little bit, here's a chart that I use in training courses here to look at the different methods. So again, across the top, continuum, hybrid, discontinuum. And we can break this down a little bit further. So if we start by going down the left-hand side here, continuum method, we can break that down into finite elements, finite difference or finite volume, and then even boundary element. So let's just talk about that a little bit. So finite element method, this is a RS2 model from rock science on the left-hand side here. This is a finite element model. And if you look closely, what you can see is this is made up of a bunch of triangles, and the triangles actually have 6 nodes each. So they have these mid-side nodes. And this allows you to get fairly accurate results with simple element shapes. The finite difference method, the true finite difference method assumes that you have a regular grid. So the middle plot here is from Flack. And in general, what you need to do is map your geometry or your problem into a true grid. The formulation is simple, but it can be difficult to match these complicated geometries into a grid. The finite volume method, so the right-hand plot is a Flack 3D model. The finite volume method does not have those restrictions. You can have these unstructured meshes, which is what I'm showing here, which does make it easier to model things with more complicated geometries. Now that's pretty much it. I mean, the interesting thing about finite element versus finite difference or finite volume is people generally get confused because they think that the finite element method always is an implicit solution, and the finite difference or finite volume method is always an explicit solution. And that is certainly not the case. I'll talk about implicit versus explicit in a second, but I'm just showing on this chart here some examples. So implicit finite element method is probably what many of you are used to in the geomechanics world, RS3, Plaxis, Midas, and so on. But it is possible to do explicit solutions with finite elements. LS Dyna is a popular example. Similarly, mostly you'll be familiar with explicit solutions in finite volume world, FLAC and FLAC 3D. It is possible to do this implicitly as well, and we've actually been working on implicit solutions for fluid flow and thermal flow in the finite volume method. So just to talk about that a little bit more, implicit versus explicit. So the middle plot here is just a very simple model of a square, basically, with a load applied to the top. If we assume that the material is elastic, we can get to the solution in one step. So on the left-hand side here, the implicit solution basically does a great big matrix inversion and gives you the final displacements in one shot. The explicit solution works differently. You apply the load and the disturbance propagates through the system until it reaches the boundaries and everything comes to equilibrium, and then you're done. And at the end, you basically have the same answer with the implicit or the explicit. You just got there in a different way. So you're looking at this and you're wondering why you would choose to do the explicit approach when it looks like, in this slide at least, the implicit approach is probably faster. The answer is that the explicit approach is better for problems that are not elastic. Well, better for problems that are a long way from being elastic. So, for example, when you have dynamics, if you have something that's deforming in large strain, or if you have highly nonlinear material behavior. So this is just an example here of a dam being subjected to an earthquake. You've got some fairly nonlinear behavior here, and then you've got these really ugly displacements going on at the top there. These are the kind of problems that are useful to solve with the explicit approach. So, okay, finite element, finite difference, explicit, implicit, whichever you choose, these are all continuum methods. Why is the continuum method still so popular? Well, first of all, it's fast. You could easily run 5 million element model on a regular off-the-shelf PC. Probably you could do a 10 million zone model right now. It's mature, and what I mean by that is it's been around a long time. A lot of people use it, so there's a lot of functionality in here. Fluid flow, thermal, structural elements, factor of safety, all these things that people want are available in most continuum models right now. You can directly specify constitutive behavior. This is very attractive, especially in soil mechanics, where people have very specific and very complicated soil behavior. And lastly, I put here easy interpretation. People like to see these contours of stress and displacement, like I'm showing here. You can slice it and dice it and get cross sections, and all these kinds of visualizations are relatively easy with the continuum method. Now, the problem is this is supposed to be about rock and rock engineering. In that case, we need to consider faults, joints, bedding. How do we do that? Most people probably do this by considering an equivalent continuum. So you assume that there are enough joints in your model that you can basically smear out the effect and just reduce the strength and reduce the stiffness and assume that it's an equivalent continuum. And a very popular way to do this is by using the Hook-Brown constitutive model. And you can get parameters by looking at your joint density and your joint quality and use that to specify the properties of the continuum. At Itasca, we have this ubiquitous joint model. And what that is it's still a continuum, but it behaves as if there are a whole bunch of parallel joints in the model. And so you have this sort of preferred weakness plane. And you can also come up with more complicated constitutive models that try to make the model behave like it was jointed, even though it's a continuum. Now, the second bullet point here is that if you don't have so many joints and maybe you have a few major faults, you can actually consider them explicitly, even in a continuum model. And I'll show an example of that in a minute. So here's an example of the ubiquitous joint model. All these little blue discs here are not actually joints in the model. We're not actually modeling them. It's still a continuum. We're just making the continuum behave as if there was a bunch of little joints in here. And then you can get the displacements and stresses and so on like you do in a regular continuum model. This is just a more complicated constitutive model that we've recently come up with to try and consider the evolution of rock behavior from, starting to fail to actually failed to, and then in the third case, actually breaking apart into some sort of aggregate, a bunch of pieces, and then you get, a much more interesting bulking type behavior here. There's a lot of detail in this model, and I won't go into it. But here's just a movie showing a mining operation, and what's being plotted here, the gray iso surfaces are representing this area where it's actually descended into this broken apart bulked material, which gives you some idea of where the caving is occurring, even though this is actually a continuum model. Okay, so then I said, if you don't have that many joints, you can just put them in explicitly. And it's possible in most continuum methods these days, at least in the rock world, to put these joints in here. This is just an example of a simple model with a couple of joints in it, and you can see the sliding on those joints. But it's still a continuum model. You can see the deformation here, but there is a joint in it. A real-world example of this was presented by Christine de Tournay a couple of weeks ago as part of an ISRM lecture. This was a model of a dam in China, and what they did was they included a whole bunch of faults and bedding planes in the model, and it turned out to be really important. When they changed the water pressure and applied the different loads to this system, they were able to see that the displacements were really dictated by the faulting and the bedding in this model. So it was definitely important to consider them. Okay, that's pretty much all I'm going to say about continuum. Now we're going to move on to the hybrid method. So the hybrid method, if you recall, is basically a bunch of discontinuous pieces, but the pieces themselves can still deform like a continuum. And so examples of this would be UDEC or 3DEC. There's also this Iratsu program by the Geomechanica guys in Toronto. There's a similar program called Elfin that some people use, and I would call all of these hybrid methods. So you might have a model that looks something like this. You've got a bunch of blocks that are stuck together. In this case, they're Voronoi. But if you look closely, you can see the blocks themselves are still divided up into little elements here, and the blocks themselves can deform. Here's an example of that. This was a model of an explosion in a subway tunnel. Again, it's a bunch of blocks stuck together. The blocks themselves can still deform. And what they wanted to see was what's going to happen when they simulate an explosion here. I suspect these displacements are exaggerated, but you can see how there's the blocky nature of this model gives you some very interesting behavior. Another example, this is an actual mine where we were looking at the support, specifically the bolts. This was work done by Triana Garza Cruz from our office. And what was happening here was that we had a bunch of undulating beds and vertical joints. So it was a discontinuous problem. And then on top of that, she also modeled this material in between here as a bunch of tetrahedra stuck together. So you can have movement on the beds, movement on the joints, and then even movement in between because you've got these little tetrahedra. And you can see in this middle plot here, these black lines are representing the cracks between these tetrahedral blocks. And then you can see these more large scale openings, along these bedding planes and so on. So, being able to include this discontinuous behavior in the sort of continuum model was definitely important in this case. So, okay, these block models are great, but now the problem is what happens if you want to have material failing between the joints? For example, in this plot here, maybe you have some joints in here, but then you've got some rock bridges, and these rock bridges actually break, and then you've got failure of this thing. These types of systems are a little more difficult to model with those blocky models. How do we go about considering that? When we get to these types of problems, now we're thinking about a true discontinuum model. So now I'm over here on the right-hand side. And if you recall, the discontinuum model is a bunch of pieces that themselves cannot deform, but the deformation occurs through the movement at the contacts between the pieces. And in this way, we can sort of model fracture propagation and things breaking apart by looking at the movement between the pieces. Almost all of these true discontinuum models use the explicit approach. These model behaviors are highly nonlinear. Things are breaking and moving. It is certainly possible to do it with the implicit approach and sort of jump to a final answer. It's much more difficult and it's much less common. One example here is DDA. This is an approach by Genhua Shi and Richard Goodman, which is sort of an implicit discontinuum approach. But most of the models that you see out there, PFC is one example. There are a whole bunch of other ones out there that are doing this kind of stuff. And I would suggest that almost all of them are doing the explicit approach. So again, similar to the block model, but the pieces now cannot deform. And what this means is that it's much more efficient computationally. We're only looking at deformation of contacts. We don't have to do the stress strain calculations for the pieces. It can theoretically run a lot faster, especially if you consider the pieces to be spherical, then the contact calculations become very simple. In this case, we do not have to assign constitutive models like we do in the continuum method. Instead, the sort of macro behavior just emerges from the fairly simple contact behavior that you specify. So I'll just show an example here. This is a good example of where the true discontinuum method might be useful. It's an old example, but it's still a good one. And this is a rock cutting. So I think this was done for the oil industry where they're interested in cutting and drilling holes. And so what you can see is this is a true discontinuous behavior, where things are breaking apart and moving and separating. This kind of thing would be very difficult to model with a continuum method. Now, again, it's possible to have sort of different scales of discontinuity here. Because this is supposed to be about rock, we're again worried about joints and joint sets. And what you can see here is it's possible to consider a discontinuum model. This plot on the left here is showing, if you look closely, you can see all these little gray spheres stuck together. But then on top of that, we have some actual joints. This is a discrete fracture network in this case. And you can do some tricky mathematics here to get sliding on these joints to make it sort of realistic, as well as the breaking and fracture propagation in between the joints. So this is kind of a neat way to consider rock material. Now, the problem with DEM, at least if you're using spherical particles, is that it really kind of doesn't behave like a rock. We know that in real life, especially crystalline rocks, you have a lot of interlocking, which is not really well represented by these spherical particles. So, how do we solve that? One possibility is to use more sophisticated contact models. So on the right-hand side here, you can see this is something we're calling the flat joint model, which basically works out the contact mechanics as if there was a sort of a flat piece of material here that resists rotation. And so you get a much more sort of interlocked behavior. Another way you could do it would be to take all those spheres and then stick them together to make clumps that are sort of non-spherical shapes. And that's what I'm showing you here on the bottom left. And it's certainly also possible to create non-spherical shapes and make actual polygonal particles. And there's an example of that. So this was a relatively simple unconfined compression test. This was a cylinder composed of tetrahedral blocks all stuck together. This is, I think, was about 30,000 blocks stuck together. And then we just loaded it in compression. And what you can see here is you get this fairly realistic sort of stress strain behavior. And then on the right here, you can see the cracking that occurs, and then the colors represent the fragments of sort of contiguous material. So again, you get this interesting, rich behavior out of these models that is fairly rock-like, just by having relatively simple contact mechanics and not specifying, macro constitutive behavior. So, advantages of the DEM method. You can observe fracture propagation and material breakage. The pieces have the potential to actually rotate and move, and this can give you fairly realistic bulking behavior or spalling behavior, kinds of things that are difficult to simulate in a continuum model. And again, you don't necessarily need to specify complicated constitutive models. Now, the disadvantages of the DEM, these famously require calibration to match the macro parameters. So again, you're dealing with these contact behaviors, and you need to figure out what those contact properties are to give you the macro behavior that you want. It can be hard to visualize if you're used to looking at contours of stress and displacement. It can be a little more challenging to visualize with these particle models. And then in bold here, now we're going back to the very first slide. Really, it's probably still too slow to run these models to do field scale problems. And by field scale problems, I'm meaning like an open pit mine or an underground mine or a subway tunnel system. It's not realistic to model this whole situation with particles. So what do we do? There are a couple of possible solutions here. We can take the discontinuum model and couple it to a continuum model. So we're only putting in discontinua in the region of interest. Another possible solution is to try and simplify the formulation. I'll show an example of that. And then the third sub-bullet here is it's possible to run a bunch of discrete element models to get a feel for the behavior that you're looking for, and then encode that into, again, a sort of a simplified version of this thing. So here's an example of coupling. And what we've got here is a bunch of spherical particles inside of a continuum model, and these things are coupled together. So what you can see is we're going to excavate a tunnel and plot the displacements, and you can see how the displacements are continuous across the boundary between the particles in the continuum. So it's certainly possible to do good and accurate coupling between the continuum and the discontinuum. And what this allows you to do is put the discontinuum in the area of interest and look at damage mechanics and cracking and spalling and things like that, which is difficult to do with the continuum. The second approach I said was that we could actually try and simplify the discontinuum model. And so one thing that we've been doing at Itasca is this idea of a lattice model. So instead of having these spherical particles that can rotate, and move long distances, we replace all of that with just springs and masses. And this makes the computation much less intensive. And we've shown that doing it this way is roughly 10 times faster than having a bunch of spherical particles. So now it's possible to at least approach doing field scale problems with these types of lattice models. The drawback here is that really this is only suitable for small strain. You wouldn't be able to use this for those cutting type problems like I was showing before. Here's an example of that. We use this approach for hydraulic fracturing. That's a program called Explicit. You can see here, this is a horizontal well with 3 injection points. And what's interesting here is that you've got these 3 fractures growing, but there's stress shadowing and interactions between these fractures. So you don't get these perfectly planar fractures. You get some interesting shapes going on here. And in fact, termination of this guy in the middle here because of the stress effects. And so these kind of things, you really need a discontinuum model to consider, these types of non-planar propagations. I'm nearing the end here, but this is an example of how you can take these discontinuum models and run a whole bunch of them and look at the behavior of them, and then encode that into a sort of simpler approach. And so what we've got here is a new program we're working on called MassFlow. And what they did was they ran a whole bunch of PFC models and then looked at the behavior and then sort of encoded that into a sort of semi-mechanical model for cave mining specifically. And so this is more or less a continuum model, but we've got this behavior in the middle here, which is based on what we've seen in PFC models, but it's not actually running a particle model. It's just using the learnings from the particle models to get the right sort of caving behavior here. And so it runs way faster than a particle model, but still gives you the kind of behavior that you're looking for. Okay, so just to finish up, I talked about continuum, I talked about discontinuum and hybrid methods. There are a whole lot of other possible methods out there that I have not talked about. I'll leave it up to you to go and research those things. One of the things that is becoming more popular is this idea of meshless methods. And so what this is you generally have some sort of particles moving through a background mesh. And this is kind of neat because it's sort of halfway between a continuum and a discontinuum. You get this sort of discontinuous behavior because you have these separate particles, but it's still kind of like a continuum. And so there are a bunch of different versions of this, smooth particle hydrodynamics. The one we've been working on is called the material point method. And so a geometry is discretized into a collection of material points, and each point has its own material properties and initial conditions. And what you can do is, again, it's sort of like between a continuum and a discontinuum. Here's just an example of a slope failure. And what you can see here is, you can consider these very large deformations. In a continuum model, probably the elements would obtain the shape such that you wouldn't be able to solve it anymore. But with these material point methods, you can look at these very large displacements and it still works. So that's the end. That's all I have to say, and I'm happy to answer any questions. Thanks for your time.